Good morning and good evening to our participants from the US and Europe, and welcome to the Forecasting 3 session of the ESIG 2020 Meteorology and Market Design for Grid Services workshop, being held online on Tuesdays and Thursdays during the month of June. I'm Charlie Smith, the Executive Director of ESIG, and I will provide a few brief opening remarks. As most of you know, we were originally planning to do our annual Forecasting and Markets workshop in Denver this month, but due to the coronavirus situation, we found it necessary to move the workshop online. The workshop was planned with the input of our ESIG Offerings Committee, chaired by Bethany Frew of NREL, and co-chaired by Julia Matoibasan of ERCOT. The committee consists of the chairs of our 6 working groups and several of our board members. We have a great set of volunteers who make ESIG what it is, and we encourage you to become members and get involved if you haven't already. Regarding logistics, I would ask you to note that the webinar will be an hour long. We will have 5 individual presentations, about 10 minutes each, and we plan to hold the questions for a 10-minute question and answer session after the last speaker. We're trying something a little different for the Q&A going forward. Attendees are requested to ask their questions through the Slido platform. You will not be able to ask your questions through WebEx. You should go to slido.com on your device and enter today's date, June 25, June 25, as the event code to ask questions of the panelists. Please note the person that you're asking the questions to. The instructions are also on your screen in the webinar announcement at the bottom of the session information box on the website, and you'll be reminded by the session chair. You'll see a thumbs up button next to the question to allow you to help prioritize the questions submitted. So please keep the questions coming during the presentations, and we will address them at the end. Recognizing the limitations of a webinar with typically more than 100 people on the lines will be muted. So again, we ask you to use the Slido platform to ask your questions with today's date, June 25, as the event code. Today, we're hosting the Forecasting 3 session, co-sponsored with IEA-WIND Task 36, on updates for best practices and tools for forecasting, chaired by John Zack of UL Renewables, with Corinna Möhrlen of WEPROG serving as co-chair. John is a senior advisor for grid solutions at UL. He's recognized as a leading authority in the application of atmospheric modeling techniques for the purpose of producing wind and solar resource assessments, as well as short-term wind and solar forecasts. Corinna is the founder and managing director of WEPROG, where she pursues her interests in operational wind forecasts with multi-scheme ensembles and international research cooperation. Both are longtime contributors to ESIG. John will manage the session logistics, and Corinna will handle the Q&A. I've known both John and Corinna and worked together with them for many years now, going back to the first days of the workshop over 10 years ago. And I consider them both good friends. John and Corinna, we appreciate having you here, and I'll now turn it over to you, John.
Thank you, Charlie, and welcome to Forecasting Session 3. The 5 speakers in today's session will provide an overview of the recent activities and future plans of IEA-WIND Task 36. Task 36 is an open international collaboration among public, private, and academic sector participants to address key issues related to the production, performance, and application of short-term wind power forecasts in order to facilitate the realization of greater value from those forecasts. Our first speaker is Gregor Giebel. Gregor is a senior researcher at the Technical University of Denmark, often referred to as GTU, and he is also the co-operating agent for Task 36. Gregor will provide an overview of the task. Gregor?
Thank you, John. Very shortly, the Task 36 has a web presence at IEA-WIND Forecasting. And we also recently had quite a number of new videos on the YouTube channel that's also to be found under IEA-WIND Forecasting. The International Energy Agency was founded in the 1970s as a counterweight to the OPEC countries and the oil shock that ensued. which in North America more was known by the long queues at the petrol station, while in Europe you had the car-free Sundays on the motorways that were the iconic image. The specific collaboration programs there's a number of specific technology collaboration programs in the IEA on a number of different topics. Wind energy is one of them. Wind energy TCP actually encompasses most of the installed capacity worldwide. US, Canada, a lot of Europe, China, Japan, Korea, with a few more in the pipeline. Very shortly, what do we say if we do short-term prediction of wind power? We start out with the numerical weather prediction, which is predicting just the wind. We usually use online data to go into some sort of a power curve model that then converts the wind to power. That can be one single forecast or an ensemble of forecasts. And from that, we get the nowadays typically probabilistic forecasts to the end users, which can be grid managers, trading, or for something else. That means that we also have a number of different stakeholders, typically Met services for the numerical weather prediction, then a whole lot of forecast providers in the center, and a lot of the end users to the right. And that's also the way how we structured the task. There's a work package 1 on coordination of numerical weather prediction improvements. There's a work package 2 where we mainly currently have a recommended practice on forecast on forecast vendor selection, forecast solution selection, that's the word. And we have a third work package that tries to find out how we can actually make probabilistic forecasts more palatable. And all of these points are going to have their own talk in the further proceedings. So if you now or after this session are interested in joining or collaborating on any kind of level or just being kept up to date, send me a mail at grge@dtudk or contact the cooperating agent Will Shaw of PNNL. Thank you.
Okay, thank you, Gregor. A reminder that questions can be submitted through the Slido, slido.com portal, and the event code is June 25, JUNE25, and we will address the questions at the end of all the presentations. So I will wear my presenter hat at this point and discuss work package 2 activities that Gregor mentioned, which is the IEA-WIND recommended practice on renewable energy forecast solution selection. So the overview of my presentation here is I'll start out with a little bit of motivation as to why we developed these recommended practice documents, and the structure of the recommended practice document set, and then the key points from each component document, and how you can get more information about the documents. So the issue that the recommended practice addresses is that even though it's been well documented that the use of forecasts to assist in the management of variability of wind and solar-based generation can lower variable generation integration costs while maintaining the required high system reliability, a substantial amount of the potential value of the forecasting is not realized due to the use of non-optimal forecast solutions by users. And the reason for this falls into several categories. One reason is specification of the wrong forecast performance objective, and I'll give an example of that on the next couple of slides. but also poorly designed and executed benchmarks and trials of alternative solutions. So you don't select a good solution and a good match for the objectives of the application. And also the use of non-optimal evaluation metrics for forecast evaluation. So all of these are addressed in the forecast solution selection recommended practice. So an example of a misaligned forecast objective from the Big Island of Hawaii is the users requested a 0 to 6 hour forecast at minimized square error for every 15-minute interval over that 6 hour period. And the resulting forecast attribute then is that the phase and amplitude errors in the small scale cloud features of solar forecasts at the 15-minute time scale result in the optimization creating a smooth forecast. In other words, a minimization of the temporal variability. And this is in order to minimize RMSE or MAE, since there are phase and amplitude errors. However, the application really needed an estimate of the variability in the midday period from, say, 10 a.m. to 2 p.m., because the range of variability would drive the need for online reserves to address the ramping caused by the variations in solar PV production. So the important thing was not necessary to have each 15-minute period correct. It was important to have the envelope over that midday period. What would be the highest 15-minute period and what would be the lowest? But that was not communicated in the process of setting up the forecast solution. So the result was that the MAE for these forecasts over the midday period was quite good, at 4% of capacity. That was 15% lower than what we would call smart persistence for a solar forecast over the entire year of 2017. But if you look on the chart on the right, which shows the midday range of those 15-minute solar generation values. So each dot on that chart is 1 day of 2017. The horizontal axis is the forecasted range, max minus min, and the actual outcome is on the vertical. And you see the forecasts are heavily biased towards low variability and don't identify the days with high or even moderate variability very well. And that was actually the prime desire on the part of the application users, that we needed to estimate how much variability there was in the middle of the day, but the forecast solution was not well aligned with that purpose. So that was really the motivation to address the forecast solution selection process. So an international group of experts have interacted under the framework of Task 36 to formulate a set of documents that specify the best practices for selecting. Actually, WIND was the target of the task, but the documents are entitled Renewable Energy Forecasting Solution, because we believe a lot of the key points made in these documents apply not only to wind, but to solar as well, and probably for other types of forecasting. So the documents are structured, or the recommended practice is structured in a set of 3 documents. The first is a selection of the optimal forecast solution. So that is the broadest document that looks at the whole process of how do you design a process to select the forecast solution that's optimal for your application. The second document is a design and execution of benchmarks and trials, which can be a part of the forecast solution selection process. But as we pointed out in part 1, that's not necessarily the best approach for all users in every situation. So while benchmarks and trials may be a useful tool, they need to be conducted in the right way and be formulated in an appropriate way to get the value from them. And then part 3 is the evaluation of the forecast and forecast solutions, which can be part of a benchmark or a trial, but it can also be done as evaluation of ongoing forecast solution that a user may have. So the current status is it's been accepted by the IEA-WIND Executive Committee. It's been published as a IEA document as a recommended practice, and it's available from the IEA-WIND forecasting website. The link is on the bottom of the slide there under publication/recommended practice. So I'll give a brief overview of what's in the 3 parts of the recommended practice series. Part 1, as I mentioned, is a selection of an optimal forecast solution. This presents an overview of the factors that should be considered in the solution selection process and discusses the issues associated with each of those factors. And most importantly, it provides a decision support tool in the form of a flowchart to assist users in the design and execution of the solution selection process. And it also provides practical lists and frequently asked questions for use in RFI or RFP in the tendering process. So it gives a lot of guidance for those not familiar with the process of selecting a forecast solution, how to go about it. Now, part of that might be a benchmark or a trial where you actually look at forecast solution alternatives and evaluate them. And this second part helps users conduct a trial that's going to produce meaningful results. And it presents the 3 phases of a forecasting benchmark or trial: the planning phase, the execution phase, and the analysis phase, and discusses the factors and issues that should be considered in each phase. But it also provides a list of pitfalls to avoid. And these have been compiled from many of the forecast users that participated in the writing of this document, and things that they've actually experienced in the course of about 10 years or more of trials collectively among those that contributed to the writing of Part 2. Now, Part 3 is focused on evaluation, and this presents the key attributes of the evaluation process: representativeness, significance, and relevance. And each of these has to be considered and addressed in order to have an evaluation that's going to be meaningful. You can often get numbers on an evaluation, but they don't have real significance and relevance and representativeness for the application that is important to the user. So this discusses each of the factors and the issues that should be considered for each of these attributes, and provides recommendations for conducting a high-quality and meaningful evaluation. So the documents were created at the end of Phase 1, which was December of 2018, and we moved into Phase 2. And the RP-related plans in Phase 2, which extends through the end of 2021, is to increase awareness of the availability of these documents and the recommended practice information in them, and obtain feedback on the usefulness of the recommended practice document series to the user community. And this presentation today is part of that dissemination of information about the documents. We've conducted a number of other presentations and open space workshops to increase the visibility of the documents. And we're looking to update the documents at the end of Phase 2 and possibly include material on probabilistic forecasts, the use and evaluation of those, and also more examples of issues and solutions. That was one of the items that we've received very heavy feedback on so far, that users like to see more examples of the points that are made in each of the 3 component documents, and how the users might apply some of the principles that are discussed in those documents. So if anyone in the audience or anyone that hears about this would like to make suggestions on what we should include in future versions of the documents, we'd be very eager to hear about that. So I will conclude by pointing out where to get more information. The documents, as I pointed out, are on the CAS 36 website, which you see listed there under publications/recommended practice. There are also a number of papers and presentations that have been made over the last couple of years. There's also a webinar on recommended practices on the YouTube channel. You can see the link to the YouTube channel on the right there under Task 36 information. And of course, I'd be happy to follow up on any questions that anybody might have. So I will end the presentation there, and we'll move on to the next presentation. Our next presentation will be by Corinna Möhrlen, who is the Managing Director of WEPROG. And the title of the presentation is Forecast Games and Experiments Initiative, an Example, Offshore Wind Power Decision Making in Extreme Events. Corinna?
Thanks, John. And hello, everybody. So I'm talking today about an initiative within the work package 3 that we have been starting at the end of 2019. And it's the work package 3 is about assessing methods and develop tools for the use and application of uncertainty forecast. And this first initiative on forecasting games and experiments has been, as John said, dealing with an offshore wind power decision making in extreme events. And I want to here at this stage also acknowledge my co-author, Nadine Fleischhut, with whom I have been developing this. She is a researcher at the Max Planck Institute for Human Development, and a psychologist that has been really bringing us into this topic of looking at more structured ways of evaluating the barriers that people may have on using applications on uncertainty forecasting. So this is just a slide showing where this belongs to in the work package, and somehow my computer has no. Okay, so I'm back. In the IEA overall picture, so the goal of this initiative really is to make experiments and investigate the potential benefits of uncertainty forecasts in decision making. And by doing this, we want to also provide kind of training tools to demonstrate the use and benefits of uncertainty forecasts. And what is important for us is that the simulations are kind of real life decision scenarios. And by doing this, really, we combine the training and the simulation together, and so people can get feedback for themselves, also learn how to use forecasts, but also we can stimulate discussion on how to develop more and different applications in the future and gain and gather new ideas on how to communicate. Because one of the issues we realized was that the communication of uncertainty forecasts has been or is still a developing area, and we are kind of at the beginning of this. So although we can say from meteorology, we know since about 30 years that deterministic methods or deterministic forecasts hide uncertainty that are inherited in every forecast. But knowing this, we still, in many areas in the power industry, everybody relies on a deterministic forecast. So then we have been looking into research in psychology and human development on decision making in weather forecasts, and we found some interesting research that really suggested that including uncertainty estimates in weather forecasts led to decisions that are better or at least more informed. So people that had to take decisions they got an increase in trust in the forecast by using uncertainty information, and it gave them in general in all the research experiments a better idea of what to expect, kind of possible outcomes, or in particular situations of decision making. It gave them an idea, feedback of when a forecast was off, why this was off. And the other thing that is really important, important finding was that the type of uncertainty forecast and appropriate communication, this is crucial, and this is also in line with the research, and that's why we wanted to generate a number of games and stuff that people can have fun doing and still learning. So what we did is we made a plot, simplified of course, but we wanted to test a typical decision situation where we said in trading the success is often dependent on the costs of the balancing power that is required, so due to forecasting errors. And often traders say that 5% of the cases or the errors are responsible for 95% of the cost. So it's the large errors, and if you can avoid these large errors, it is worth much more than just a 1 to 2% improvement of a general forecast. So a similar situation would be, for example, in a control room where the control staff has to decide whether there should be curtailment. That would be a similar situation, curtailment costs, because you have to refund the renewable energy that is curtailed. So it could be used in different ways, but we decided to make a trading experiment, and so we made high-speed cutoff cases. That means that we looked at an offshore wind farm that came to the limits of where it can produce power around the 25 meter per second, and looked on forecasts in 12 cases, and the users had to decide whether to trade 50 or 100%. And the decision tools they got was 3 deterministic forecasts showing the wind power and wind speed, and the ensemble forecast showing wind power and wind speed, including 9 uncertainty bands. And to take this question now that I got previously, the participants are fully anonymous. That has had to do with that we made it relatively ad hoc, and because of the data protection stuff, we could not get any kind of information from the participants. The first about 30 participants were from the workshop, and the remaining are just anonymous. So we don't know whether they are experts or non-experts. When dealing with extremes, we have to remember 2 important features. So we have to define the thresholds. And in our case, we looked at a high-speed shutdown, so the cutoff wind when the wind turbines shut down. And usually we say this is around 25 meter per second, but this around is something that really somebody that has to make a decision has to be taken serious. So we saw, or anybody that works with such problems knows that it can be between 21 and 27 meter per second before a wind turbine shuts off or an entire wind park shuts off. So this is something that the participants of the game had to take into consideration. And then for the methodology, we chose a physical ensemble prediction system with 75 members, the MSEPS system. and that was to ensure that the uncertainty information that was given was really valid in every forecasting hour. So this is how the forecast, the deterministic forecast look like. You can see on the upper figure there is wind power, and in the lower figure the wind speed. So there was only one wind speed forecast, and the threshold around 25 meters per second, and then the three forecasts, and you can see this is not an easy decision to make. If you then look on the uncertainty forecast, you get a different picture. We had both for wind speed and wind power percentiles, and there you get a much better picture kind of what is happening. But this was not in all cases like that. So there was still kind of a decision to be made, and this was the cost function. And I think this is not so important right now. There was a loss when there was a high-speed shutdown and you traded 100%. So you could gain more when you were right, and you could lose more when you were wrong. And then when you were more conservative with the 50%, and you didn't lose anything, but you wouldn't also gain as much. So the analysis summary, we had 120 participants, and what we found was that it was a slightly higher income and more correct decisions that were made. And but the interesting thing was that it was really less risky decisions that were made. And another interesting thing was that the participants changed their mind in about 18% of the cases. So they got first the deterministic, and then afterwards the probabilistic, and then they could change their mind. So this doesn't look like very much, the 18%, but 91% of the participants changed their mind at least once when they saw the probabilistic forecast. So the results of more of the results can be seen at the end of the presentation when this will be public, or there is a link also where they are still online. I have to say that it needs further testing, and this is also what we are going to do now. So we can see that uncertainty forecasts show what is hidden in deterministic best guesses, and the decision making is not more simple, but it's more informed and more honest. But we also saw that there was really an education and experience needed in how to communicate such. So the next questions we want to answer in this round of experiments that we are planning now is, can the probabilistic wind power forecast really improve decisions? And does feedback from uncertainty forecast make it easier to learn to make decisions? And how good can people then transfer knowledge to other decision tasks? So that's what we're working and on next. And I'll finish with, if anybody is interested in participating in larger experiments, then please contact me. You can also find my contacts on the IEA webpage, or through Gregor or Charlie to get in touch with me. Thank you.
Thank you, Corinna. And we'll move on to the next presentation. And the presenter will be Jeff Lerner, who is starting a new position as Business Development and Project Manager at ENFOR in Denmark. And the title of the talk will be Data Format and Communication Standards to Support Forecasting Services. Jeff?
Hello, everybody. Please grab a cup of coffee. Might need it for this presentation. I have to admit, this is not the sexiest discussion topic, but it's very important. So I'll be talking about data format and communication standards here for supporting forecasting services. So this is actually a quite important topic because it really gets to the heart of the cost of forecasts and the improvement in forecast. So let me down the slide here. This is just a brief summary of what I'm going to be talking about for the next few minutes. Talk about where this fits in with the IEA Task 36. What is it we're trying to solve? What has been done to date? Examples, the current approach, and future work, and how you can get involved if you're interested. So IEA Task 36 Work Package 2. This, we're in phase 2, as was discussed in previous talks. And this falls under the subtask 2.4, which is talking about the collaboration and standardization with the IEC and the need for this collaboration, and will result in a recommended practice like some of the other IEA tasks. And there's a link to the bottom there where you can look further. Okay, so what is it, the problem that we're trying to solve? So currently the situation is between the forecast providers and the forecast users is there's a lot of communication back and forth and exchange of data and a lot of reinventing of the wheel of what has already been done. So I imagine there's quite a few forecast users and forecast providers out there listening today. And you'll know that when you're setting up a forecast, a lot of times there's miscommunication. There's not clear terminology on what the different details of the forecast parameters are for setting up a forecast system. And there's not really a standard way of exchanging data. In fact, all those I list there, the REST API, FTP, email, and thumb drive, are things I've actually experienced in the past. I'm not kidding you when I said I've gotten data on a thumb drive from a client before. It was actually FedEx to me overnight, and I couldn't access that data until we got an NDA signed and a password, and it was just like, this is taking a long time. There's got to be an easier, more standard way. So there's a lot of potential for this rework, miscommunication, and it's very time consuming. And if that time could be better spent on just forecast improvements, boy, that would be great. And from a user standpoint, forecast user standpoint, a lot of times you don't want to have to change forecast providers because you have to go through this process of exchanging data and changing your scripts. And it would be easier if everybody was singing from the same page, right? So really, ultimately, we're trying to bring down the cost of getting renewables cheaper onto the grid by making forecasts more seamless and quicker to set up. Okay. So that's the problem we're trying to solve. And here's a good example. And many people out there will understand this one. How would you succinctly and effectively describe in words the time series date time interval? In my experience over the decade of doing setting up forecasts, you know, is it a leading or is it an ending period? Is it instantaneous or an average value? And if you're talking about a forecast time series, that could be very different than if you're talking about a measurement time series when you're talking about the date time interval. So this is just one example of many where you have to have this detailed communication. A lot of times you're educating a forecast user, or you have to be on the same page, maybe in a phone call or something, just to get over this topic. So enumerating this information and providing examples help define. And so this is just one great example. Let's go down here. Okay, so what has been done to date? Are there existing standards? Can we borrow from other things so that we can make a recommended practice for energy forecasting? ENSOE, this is the European TSO organization, is currently using a standard, and they have it very detailed. If you go to their site, you'll see that they have detailed information about energy forecasting implementation. So it's very good right now because you can go there, the documentation's online, they're using a common information model, And it's already being used, as I said, so this is already in practice. Some of the weaknesses is not maybe applicable to all forecast users, so it might be expensive to implement if you're like a small developer, or if you're a small utility. You have to have a certain level of programming experience to get to this kind of standard that's used right now by the TSOs in Europe. But it is a standard, and it actually works right now quite well. The IEC 61400-12, this has to do with power performance of wind turbines. This is a standard that has gone through the process of like actually getting it to a phase where it's in a standard that anybody can access globally, internationally, and it's recognized. It's a great model to follow in this example of trying to get a recommended practice to a standard for energy forecasting. Right now, it's not applicable to renewable energy forecasting. It's been done with the resource assessment in mind, but it's a great example we could follow. The IEA Task 36 Phase 1, so this was the work that was done pre-2019. As John showed in a previous presentation, there's this recommended practice on executing benchmarks and trials. Very applicable to renewable energy forecasting. It has guidelines, metadata, sample schemas in there for data exchange, but it doesn't go far enough, I would say, with as far as having details on the data structure, the definitions, units, and it also doesn't link to a standard. So you couldn't like look at the terminology and map that to a standard that's internationally recognized. And there's also a couple other newer ones that I've been learning about more recently. Well, DOE actually has been funding the SIP2 project on the open source evaluation framework. This is the Solar Arbiter, which many of you are familiar with. This is a great working model that has an API framework. It's a RESTful API, so it's very well recognized as kind of a standard in that sense for exchanging data. And it's extendable to wind, and it's publicly available to open source, very well documented, easy to understand. One of the weaknesses, its future is uncertain after maybe the DOE funding runs out. Maybe there'll be some more sponsorship of this work, but it is open source, so it could be adopted. And it's not currently mapped to an existing standard that I'm aware of. And then finally, the Serif ontology. This is about smart appliances reference. This is a European standard that's done by the ETSI, the European Standard Organization, and the EU industry standards. So this has to do with demand response energy communications. It's highly extendable. It's using a lot of modern framework for like schemas and definitions. And it's very forward-looking. This is really probably the most advanced in terms of the energy transition to distributed resources and everything being interconnected with smart appliances. So it's really got a little more of a forward look. And the one drawback right now, which I'm sure we might get addressed in the near future, is not as known right now in the ISO and TSO space. And it's really geared for more of the distributed generation currently. However, there is some funding for this interconnect project, which is a major project in the European Union to get more interoperability with and energy management with more for energy applications in the grid. So this is really exciting, future-looking work. So this is kind of what has been done, what we can borrow from for the recommended practice. And I wanted just to show you a quick example. This is from the ENSO-E implementation guide. And it's very nice. You can follow some of the attribute value tables to an actual definition table, like a code list. So you can take a term and find out what does that mean. And like in this example, I was using coordinate systems. And everything is well defined. There's a code for everything. So it's very mappable and replicable, and it can be implemented programmatically. There are other examples out there. I'm not going to go into the recommended best practice. You can check out online, but it has examples in that recommended practice. But when we're talking about energy forecasting, short-term energy forecasting for renewables, there are some main data layers that we're talking about. So think of these columns here as there's common data that we, as forecast providers, commonly request. So there's master data about the wind plant or the solar plant, talking about the site, the coordinates, the capacity, that kind of information. Then you have a column here called dynamic data, and this is more has to do with the power data that's coming out of a SCADA system, the real-time measurements, and any future availability about the plant, which is going to be changing. And this could be in an operational real-time, or it could also be historical data. So there's information we need to gather there and have a recommended practice for how to make that standardized. And there's also the forecast itself. You know, there's RESTful APIs, there's CSV files, and so there's information describing those. And then the metadata about the setting up the forecast system. Okay, moving right along. Our current approach to looking at this is we're dividing it kind of two levels. These are kind of corresponding to the different users. So level one would be more along the lines of a small developer or a small utility where we need to get some standards and definitions, but they might not be able to get to the level two yet, where it's fully programmatic and repeatable. So that's how we're kind of approaching this. We're kind of breaking up in these two levels. And we're also working on getting further inputs from other groups. So looking at getting forecast users more involved. Currently, it's kind of being driven more by the forecast providers. So we'd like to, if anybody out there is a forecast user would like to get involved with this effort, please email me or email John or Gregor. And we want to get a more structured process in terms of this documentation so that you could follow along in the review and the versions. And then, you know, get it through some of the review process and then coordinate with other groups that are out there that are looking at standards like the IEC, the ETSI, Solar Forecast Improvement Project, ESIG. And then finally, yeah, imagine the future here where we don't have to spend so much time on reinventing wheels. That's really what we're talking about. And I can't say that enough, is like how much time today forecast providers are spending on back and forth communication and forecast users who might not try the best forecast out there because it's just, there's so much work in actually setting up a new system for a new forecast provider, exchanging all this information. So imagine, you know, a world where we can focus as forecast providers on the accuracy issues or maybe atypical business requirements, and the consumers can just interchange between different forecast providers and figure out, you know, which one provides the most value. That's really what we're talking about. Simple as that. I think I'll leave it at that, John.
Thank you, Jeff. And we'll move on to the next presentation. And our next presenter will be Will Shaw, who is the Earth System Measurement and Data Manager at Pacific Northwest National Lab. And the title is MWP-WIND Forecasting Benchmarks. Will.
Thanks, John. And good day to everyone. The topic that I'll be talking about today involves a focus particularly on numerical weather prediction models. And I want to acknowledge my co-authors on the talk, Carolina Droxel of the National Renewable Energy Laboratory and Larry Berg of Pacific Northwest National Laboratory, who are providing a lot of the key leadership in the material that I'll be discussing today. So we have been going in order of a permutation of the task numbering for task 36. Work package 1 is really oriented toward developers of numerical weather prediction models and users, operational forecasters who use these models. There are a number of subtasks within this that have to do with collecting data to evaluate these systems, and to initialize them. The subtask that I want to focus on today is subtask 1.3, which is verification and validation of improvements in numerical weather prediction modeling. And there are some deliverables that are involved that have to do with trying to bring the community to a common framework for the application of what we call verification and validation to evaluate these model improvements. The work really, as we have initiated it, is looking to take advantage of some of the very rich data sets that exist. For example, the Perdigao experiment in particular of the New European Wind Atlas is a really rich data set. In the United States, the second wind forecast improvement project involved a nested sampling reminiscent of grid nesting within models intentionally, nested sampling of the atmosphere and complex terrain in an area of the northwestern United States known as the Columbia Basin that is also home to now, I think, in excess of 5 gigawatts of wind power. And the idea was to address some of the physics issues that we know are really outstanding in these numerical weather prediction models. One of the motivations for this IEA task, for the work package, is the recognition that on occasion there have been reproductions of experiments in ignorance of existing data sets. So part of the idea is to identify data sets that can be broadly used by the community, not just experiment participants, to evaluate improvements in numerical weather prediction models. The second wind forecast improvement project has been a very productive study. In 2019, there was a series of 3 overview articles in the Bulletin of the American Meteorological Society. So I would point you to those if you would like to look into the study in more detail. Numerous other scientific articles are also coming out of that. But it is a rich data set and I think a good source of validation. So as part of, and more to the focus of this talk, as part of the Wind Forecast Improvement Project in the Columbia Basin, we sought to apply formalism of what is known as verification and validation for NWP, or 2 NWP models. This was not invented with WFIP2 and in fact has been developed at weapons laboratories in the United States as a way of evaluating nuclear reactions and when it can be difficult to actually make measurements. But this is a formalism that we thought would be very valuable to bring a framework to the community that could be broadly used so that when people evaluated models, they would know that they were doing things in a common way and that it would result in more apples to apples comparisons, if you will. So the objective for verification and validation in WFIP2 was to provide repeatable metrics-based assessments of the models involved. The High Resolution Rapid Refresh Model, or HRR, is based on the weather research and forecasting model that is broadly used in the atmospheric sciences community. It is the model that NOAA uses for forecasting in the US. And the idea then was to verify the model, which specifically means making sure that the code that you have written is actually calculating things the way you expect. It has nothing to do necessarily with whether you're getting the physics right. That is involved in validation, which is the determination of the degree to which the model, after you have verified its calculations, makes calculations that correspond to reality. That is summarized in its application to WFIP2 in a report available from NREL, led by Carolina Droxel and applied to the WFIP2 study. In terms of the overall approach, I will not step you through all of the boxes on this slide, but I wanted to point out that we began with weather taxonomy, the identification of key phenomena that are known to cause particular difficulties for weather forecast models. And one that's indicated in the center top of this little box in the upper left is the cold pool. That happens frequently in complex terrain where large or small depressions will trap cold air. The wind will be relatively calm and will eventually be eroded by a weather system. And as the high speed or the strong winds above the cold pool wear away at the cold pool, eventually those winds will pass into the rotor layer, and that happens very rapidly, causing a wind upramp. And it's a notable challenge, one of several notable challenges still for numerical weather prediction models to get that right. So these phenomena were cataloged in an event log, which you see indicated in the upper right. And then we used this verification and validation framework in conjunction with a framework that NOAA has developed, known as the Ensemble Verification System, and applied key metrics such as the 80-meter wind speed, calculated wind power, bulk rotor layer statistics, and the wind ramp metric provided by NOAA to evaluate the observations and the models in WFIP2. Let's see, yeah. So in terms of the plan for this benchmark, there were several things that we learned from WFIP2. There was a case study tested early on, which was very revealing, in which the various teams that were going to be doing validation received a test time series with hourly timestamps. Everybody used their own scripts and then provided results for an evaluation. And the outcome was that there were different results due to wrong interpretations of the timestamp. Jeff referred to this in the communications talk just ahead of this one. And different averaging techniques in the horizontal and vertical, and a variety of other differences. And this is a major motivation for task 36. So the work that we are doing under this task in work package 1 is really working on developing a framework that can be used commonly by investigators. We've selected a case study from WFIP2, and we want this to be reproducible by participants. We have selected to exercise that using the WRF model, which is open source, and anyone can run it. Benchmark output is being provided both from control and experimental runs, which are the improved physics from WFIP2, and also corresponding observations from the field study, and then again providing the validation framework. The case that we have selected is a mountain gravity wave case. One of the things that we learned in WFIP2 is that gravity waves in the atmosphere generated by mountains, and the Cascade Mountains are to the west of the figure that I showed early, can actually modulate the winds at the surface and therefore the power production. This is a documented case now. There's a publication in review, and so it's well supported by analysis. And so as part of a benchmark, the team will be providing WRF setup files, observations over a 24-hour period to start, and documentation. And then we have begun engaging the Task 36 broader community in reviewing the concept and then in exercising the framework that we'll provide and the extension for it. In terms of the dissemination then and how people will be able to use this, we are using the Atmosphere to Electrons, which is a program under the U.S. Department of Energy that has developed a data archive and portal for all field studies, including WFIP2. So the WRF setup files and observations for validation will be downloadable directly from that site, and that's again freely available to anyone. The validation framework will be beginning with relatively straightforward statistics that I indicated earlier. This can be amplified as we see utility, and will include the NOAA ramp metric, which is, I think, a unique metric. The communication of the framework, we have decided will be, and again, this is based on discussion and broader input, will be via GitHub, and we're going to use the Jupyter Notebook framework. We had discussed R code because many people use that also in the industry. but it seemed, based on preliminary discussions fairly broadly, that the Jupyter notebooks would be a place to start. These allow people to actually go to GitHub, get the notebook, which has the code for doing the evaluation, and they can run it on their own, and they don't have to be necessarily part of the team doing this. The documentation will be reports and journal articles and perhaps a recommended practice, but mainly there will be an invitation to collaborate. As we continue the development of this, we are looking to broadly publishing a formal framework around the end of the calendar year or early next year. And at that point, we will invite the community to exercise this and to help us by writing their own additions to the framework to extend cases. But this will help bring a uniformity to the application of metrics to the validation of numerical weather prediction models used in wind power forecasting. So that is what is going on in the numerical weather prediction corner of Task 36 under Work Package 1. Thank you very much.
Thank you, Will. And we'll proceed to the question and answer session. We're right at the top of the hour now, so we will extend the session about 10 minutes to address questions. A reminder, questions can be submitted through the slido.com platform with the event code June25. So, Corinna?
Yes, so thank you all the speakers and for the presentations. We don't have so many questions, so maybe it's also 5 minutes will be enough. But one of the questions that has gotten most hits is actually for myself, so I will quickly answer that. It's about whether we considered forecasts that directly match the penalty function. And yes, we did, if I understand the question right. So what we try to do in this first test is that we had some examples that where it was really difficult to know where you really took a defensive or a risky decision. So in first place, we just wanted to have something that is fun, but that we can also see, do people change their mind if they get more information? And so there were a number of cases where it was really important to see the uncertainty forecast, to know that you would go do a really risky decision. And that's where we saw that people changed their mind once they saw the uncertainty forecast. And to take one of the other questions also, we didn't consider any onshore. It was just an example. And we will make more examples, more games, more experiments, where we may also take onshore, where we may take solar forecasts, etc. And that brings me to the solar arbiter or solar forecast arbiter project that there were a number of people saying that could you tell about that? I think it has been mentioned now twice. The solar arbiter really has taken some of a number or most of our recommendations. So really, it has been kind of a collaboration between us, and it's nice to see that the first project has actually taken on our recommendations, and we are working closely together with them to when it's extended, that their experience flows into our recommended practices and vice versa. So then we have a question to Jeff that was, could you imagine that the data exchange standards for the forecast could also become a part of the SCADA standard? I mean, everything is SCADA in a wind farm or solar farm, and could this standard not be used for forecasts, for having a easier exchange?
That's an excellent question, and I would say yes. I mean, if you think about it, even smart appliances have some form of SCADA. If you think about it, so that's something that's a great suggestion, and I think we should probably maybe talk to some of the EMS providers like a Siemens or ABB and figure out if there is a a standards committee there. That's my initial thinking when I hear that question is like, wow, that actually makes sense. Maybe as part of the recommended practice, might not address all the forecast complexities, but at least the data part, for sure.
Thanks. So then there is one question that has come to John. What sources of uncertainty do you typically associate with a given benchmark scenario?
I think the sources of uncertainty are related to the three attributes of the evaluation that I mentioned, representativeness, significance, and relevance. To give an example, like the Hawaiian example that I provided in the presentation, uncertainty comes into the selection process when those attributes are not properly considered. So relevance, for example, if you have a metric that you're using to evaluate the forecast, but that metric is not appropriate for your application, then you're evaluating the forecast in a way that's not going to tell you very much about how valuable it is to the application that you have. So you create an uncertainty that way, that now you have evaluation results, but they don't really tell you what you need to know. And there are other ways that can happen. We're talking about representativeness. If you don't have a good sample, so for example, you have a high variability wind season and a low variability wind season, and the high variability is more of an issue, but you run your trial or benchmark in the low variability season, say in the summer, and the winter is the high variability season, then you create an uncertainty because you're using evaluation from one season to represent another season. So you don't gather much information, again, about the factors that are important to your application. So the uncertainties come into play in the evaluation process. So we're talking about evaluation uncertainty here, not the forecast uncertainty itself, which is a separate issue related to probabilistic forecasts. But how you design and execute the selection process will create uncertainties in those three areas that I pointed out. And I think the emerging tool that's been talked about, the Solar Forecast Arbiter, has the potential to be a very good tool for users to minimize some of these uncertainties in what metrics are selected, how they're computed, getting representative samples, and so forth. And so I think that tool, should be looked at, and it certainly embodies a lot of the recommendations in the recommended practice that we put together. So as it goes forward, I think it has a lot of potential to help users.
Okay, thank you, John. So the last question was something that I have a little bit difficulties understanding who should take the commercial hit on deviations from the schedules. I think that is a longer discussion. Is anybody of the panelists want to take a quick 10-second get on that? Go ahead.
Well, 10 seconds is probably a bit short, but in the end, whatever you put into the system should have all the benefits and disadvantages of that technology-specific item connected to it. So the difficulty to predict wind power or solar power needs to be attributed to the wind power or solar power provider, just like the difficulty of not being able to provide coal power without CO2 needs to be put as a burden on the coal-powered power plant. So in the end, I think it's the wind solar plant operator and the one that gets the market revenue from the wind plant that needs to take the hit. And that also means that if they take the hit, then they are also trying to get better at it and have an incentive of getting better at prediction, which is good for all of us.
Okay, thank you, Gregor. And with that, I'll give back to John to close the session.
Thank you, Corinna, and that's certainly a question we can discuss for quite a while, but I think it's about time to wrap it up. So I would like to thank our panelists for their great presentations and discussion today, and thank all of you for your participation. This has been a very timely and interesting session. I think it has provided some food for thought for all of us and a few ideas we can take home. Now, for those of you that are concerned about the dreaded webinar withdrawal syndrome, I would like to remind you that there is one more technical session in this series of workshop presentations that will be held next week. The closing plenary session is on forecasting and operational challenges during the coronavirus. It will be held next Monday at 4 p.m. Eastern Daylight Time. You can find the registration information on the ESIG website, and you are all invited to attend. Thanks again for your participation. Stay safe, and we look forward to seeing you then. Bye.